Hello students, welcome to a new lecture. Last lecture we had discussed this second problem. Now there are a lot of problems yet to be discussed in this particular chapter. But some of the problems, if we look at it, it is clearly out of syllabus. Some of the others, actually, some parts of those are still there in syllabus. But what I feel will be more appropriate is there is one more topic in this chapter that needs to be completed as part of syllabus, which is plate with holes. So I guess after we had completed that particular topic, we can come back to these problems and see what are the additional problems that we can solve. Okay, so let us try to complete the topic of plate with holes. Now, this particular topic, actually, I had started it I guess, the last class before we departed for midterm break. So, what I said was, see, when you have a plate or any structure with a hole, the stress distribution around the hole changes greatly. For example, even if you take this particular plate, which is subjected to uniform tension on opposite sides, and if you have a circular hole, let's say, so actually this is an exaggerated image. The actual size of the hole will be very less. So if you have a hole like this, we had already seen that the stress distribution around the hole changes. It is not uniform. So actually, uh, when you apply a uniform tension like this, you expect uniform stress distribution. So that is valid at these locations, but at the hole location it is not uniform. So as you can see rightly from this particular figure, the stress distribution varies like this. So it is high closer to the hole, and it is lesser than average, uh, lesser away from the hole. Now let us look at how we can solve this particular problem of plate with holes from the principles of advanced solid mechanics that we have learned so far. So this is the problem. You have a plate which is subjected to uniform tensile stress S on two opposite faces. So let's assume XY coordinate system for the plate. Now this particular plate, since I had assumed a circular hole, so which I again am repeating it, the size of the circular hole is actually very small compared to the overall plate, but for teaching purposes I had shown it as an exaggerated hole, just like what we have in this textbook. So in this case, what you can say is that we agree that the stress distribution will vary closer to the hole, but as you go further away from the hole, the effect of the hole diminishes and the stress distribution tends to be normal. So the disturbance in stress distribution happens only closer to the edge of the hole. So let us imagine a large circle with radius b, which is concentric with the original hole in the plate. So the hole in the plate has a radius a. Did I mark it here? I think I have. Yeah. And the radius of the larger circle, which is within the plate geometry and which is concentric with this smaller circle, is b. So here we have two circles, means it is an ideal scenario to use the polar coordinate system that we have learned. So for the overall plate geometry it is the XY system, and for the holes we can use polar coordinate system. So this is the problem that we are trying to solve, where B is much greater than A. Now as we discuss, the effect of the hole will diminish at B because B is very large from A. So that is also a consequence of Saint Venant's principle. So anyway, let's not discuss that right now. But the stress at B will be fairly uniform and independent of the effect of the whole. Now uh, so a equivalent to analyzing this problem, it will be sufficient to analyze this particular problem, one circular circle with another circle. So this is a circular plate with a hole, circular hole. Now this particular external tension at both sides, they should be the effect of that, it should be transferred on the outer circle. So now what we are going to do is, this plate problem, instead of analyzing this full plate, we are analyzing just this plate, two circular hole, one, or in other words, annular disk, one full disk with a circular hole. Now this particular external tension is in the Cartesian coordinate system. We have to transfer into the stresses in polar coordinate system on the surface of the circle. So for that we will use the relationship between stresses in polar coordinate system and stresses in Cartesian coordinate system, which we have used when we discuss or when we derived the formulas for problems, equations involving polar coordinates. So you can refer back to my notes that I use. So this is the expression here. C is, I have written it in short. So C stands for cosine, S stands for sine. So sigma r, sigma theta, tau r theta are the stresses in polar coordinates. Sigma x, sigma y and tau xy are in Cartesian coordinate system. So at r equal to b, what happens is, so in this particular problem, sigma x is s. So this is sigma s, sigma x. So sigma x is s, sigma y is 0, tau xy is also 0 because there is no shear force in this plane. So using sigma x as s, and with the with these trigonometric quantities, you will get sigma r equal to s cos square theta, only this part of the expression. Tau, so sigma theta is non-existent. This is discussed in class because this is a phase which is directly normal to radial direction. So in this phase there will be only sigma r and tau r theta. There won't be any sigma theta. And tau r theta, if you substitute sigma x equal to s, you will get minus s cos theta sin theta. Now s cos square theta, you can write it using trigonometry as half of s into 1 plus cos 2 theta. Similarly, you can write minus s cos theta sin theta as minus half s sin 2 theta. So in effect, this particular problem, now we are going to, is equivalent to analyzing this particular problem with this particular loading. So it looks something like this: a circular plate with a small circular hole which is subjected to stresses at its boundary as this: sigma r equal to half into s into 1 plus cos 2 theta and tau r theta equal to minus half s sin 2 theta. So this is the problem that we will analyze. Now this particular problem, now this just by seeing this, it might bring back some memories in you, like immediately after we discussed the problem of polar coordinates, we had discussed problems of circular and annular disk in which the stresses are independent of theta. Here the stresses are dependent on theta. It is a little more complicated expression, but the shape of the plate is similar to that. Now using superposition, this particular problem you can write it as sum of two problems. So here if you see, sigma r has two parts, s by 2 and s by 2 cos 2 theta. Similarly, tau r theta has minus half s sin 2 theta. So using the principle of superposition, assuming that everything is within elastic limit, you can write this problem, you can write the solution of this problem as sum of these two problems. One problem in which there is this S by 2 sigma r, radial direction stress as S by 2, which is constant independent of theta, and another part which is dependent upon theta. So here S by 2 we already have taken it here, so remaining you will have S by 2 cos 2 theta, so that is what you have here, and minus F S sin 2 theta. So you can write the total solution as sum of these two problems. Now this particular problem now becomes very similar to the circular and analytic disk problems which we have solved, which were independent of theta, right? So let me go back to those expressions. So let me quickly see. You remember we solved this kind of problems. So here the loadings are independent of theta. Okay. So when you have a constant external pressure and when you have a constant internal pressure, we had already arrived at the expressions. So these are the expressions. Sigma r equal to, so it depends basically on internal radius A, external radius B, and internal pressure Pi and external pressure Po. So here they have assumed that the external pressure is acting inwards and internal pressure is acting outwards or into. So this is the stress directions they assume. So in our case it is acting outwards, which is negative to what was assumed. So when you apply this particular equation to this problem, you can see that internal pressure Pi, that is 0, and external pressure PO, P outer, it is negative S by 2. Okay, so that is what I have done. Internal pressure is 0, external pressure is minus S by 2, pressure or stress, however you call it. Now the expressions for stresses are already there, so you substitute it here. Pi is 0 and Po is minus S by 2. So if you substitute that, sigma r and sigma theta simplifies to these two expressions. Okay, so this is the solution of this part. So where the stress is independent of, or external loading is independent of theta. So this total solution of the problem of plate with hole consists of these two parts. So second part, the solution of second part, and how we combine with the solution of first part, and how the total solution is interpreted and all, we will do that in the next class. Thank you.